Thanks to the organizers for putting together this conference, this workshop. The program looks extremely exciting and I'm happy to be here. The work I'll present is mainly been done at the University of Bonn. I've moved in the meantime to the University of Kaiserslautem. Usually, so that's not the physics building in Bonn. Usually people show the building of their institution. In Bonn it's just too embarrassing to show, so I show the main administration. That's the castle in Bonn, and when Bonn was the capital, the big demonstrations were here on the meadow in front. And just before leaving Bonn, I learned that every professor has the right to feed his cow on this grass. So I'm not sure about any of these rules in Kaiserslautern, but I don't have a cow. So what I'm going to tell you today, and you've seen already some introductions, is the combination of two different worlds in neutral atom quantum physics. So we have two very different approaches looking either at large systems, for example, Bose-Einstein condensates or other degenerate gases in optical lattice, and they've proven very powerful in, for example, simulating effects from solid-state physics or other quantum effects. Because coherent many-body interactions, they're there, and they're for granted at the moment as soon as you enter the degenerate regime. However, I still say that the high-resolution single-particle manipulation is challenging in these systems. On the other hand, there is the world of single-particle physics, and I will devote my first part, as you'll see, to introduce you a little bit to the tools we have developed to control individual particles. And here is a picture of 8 cesium atoms sitting in their pockets of a standing wave, and this system has been engineered for every atom to sit exactly at the lattice site where it should be. And in these systems we can, as I'll show you, not only control, prepare and detect them at certain lattice sites, we also have access to the quantum degree of freedom. However, the challenge in these systems is the interaction between two atoms. At the moment these atoms are still too hot, so that coherent interactions are not visible. And I'll show you that the approach I am now pursuing aims on combining these systems so that both approaches will profit from that. So the first part is devoted to the tools and achievements we have made in Bonn in controlling single atoms, and then I'll show you how both worlds can profit from combining these approaches and immersing single neutral impurities into an ultra-cold gas. So in the first part is the question, how well can we prepare and detect these individual atoms? And so I had to cut somehow 15 minutes, and now you'll get a tour de force to the tools we have developed in Bonn. And the first is, we have also developed a method to detect single atoms with sub-diffraction resolution in an optical lattice. And for example, if we take hundreds of images of up to 30, 40, 100 atoms and look at their mutual distance, and make an histogram of how often we see a certain distance, then we see with the methods we have developed in a one-dimensional lattice, we reproduce here in this histogram very well the optical lattice, even down to nearest neighbors. And the diffraction here in this case is at the point of 4 to 5 lattice sites. So we go well beyond the diffraction. And what you see here at 0 distance at the same lattice site, that is what Stefan told us. That's just these light-induced collisions. As soon as you have two atoms at the same lattice site, you illuminate them with near resonant light, they'll immediately get lost in our tight traps. So that's the first. We can detect the atoms with high resolution, but we can also prepare them at certain lattice sites, and that's just a demonstration on how we can inscribe frequency information of, for example, a microwave pulse into the position of atoms. If we fill our optical lattice with lots of atoms, we'll get such a fluorescence image. Here, for example, if we now apply a magnetic gradient field along this lattice and apply a rectangular microwave pulse, then we'll promote atoms to different spin state, and the sync function, the sync spectrum of our pulse is inscribed now in the position distribution of the atoms. And if we now narrow, for example, this pulse width or the spectral width, then we can really address single atoms. And for example, this row of 8 atoms has been just written by this way, applying 8 microwave pulses at the respective positions. We can, however, also control quantum degrees of freedom, and this is an example we have done where we entangled the internal degree of freedom, so spin state of the atom with its position, prepared coherent superpositions of an atom being to the left and to the right, and we were able to realize the so-called quantum walk, which shows a ballistic transport rather than a diffusive as in the classical random walk, and we were able to follow the evolution from a quantum behavior and saw the quantum to classical transition here to a random walk. And as I said, if you have any questions to any of these, just ask in the end and I'll be happy to tell you more about it. We were also able to exploit or to explore the motional states in the optical lattice, and to drive coherent transitions on the carrier and sidebands between two spin states. And the big thing that we were able to do is that we were able to engineer the coupling strength of these transitions. And in ion traps, usually the carrier transition is the strongest and the sideband transitions are reduced by the Lamb-Dicke factor. And we're able in our system to engineer the Lamb-Dicke factor, which is shown here. And for example, we can make the carrier transition, which is shown in green, to have the same strength as the red or blue sidebands, or to completely suppress the carrier, and to use now the motional state, the motional vibrational states, also as a qubit resource for any quantum physics experiment we want to do. So this is just to show you we have single particles under control. We have high degree of control over the external and internal degrees of freedom, and we're able to coherently manipulate them. I want to show you one example, some recent results on a single trapped atom interferometer that we've done, just to show you that this can be really something useful to explore some quantum effects, for example, close to surfaces. And the idea there is the following. We have single atoms trapped here at the side of an optical lattice, which is indicated here at certain, with the dots. The internal degrees are here encoded in colors as red and blue. And we're able to prepare the atom in a coherent superposition of these two internal states. And we have developed a method to entangle this internal degree of freedom with the position of the atoms and delocalize the atom for the blue spin state to be on the left and the red spin state to be to the right. And that means now we have a coherent superposition of an atom being to the left and to the right. There they can acquire some phase difference, then we can recombine them and read off this phase difference in some Ramsey type interferometer. And that's very analog to a Marsena interferometer, where, for example, two light beams travel along different paths, and in the end you read off the phase difference as the interference pattern being bright or dark. The big advantage of this interferometer is that it's completely discrete. So you can translate any operation into some block here, either a beam splitter operation into some microwave pulse, the transport into some shift operation, and you can reassemble and reshuffle these operations at will, and you can design the sequence such as to investigate, for example, decoherence effects, to explore some other effects like have very strong delocalization distances and bring one part of the wave function, for example, close to a surface. And here you see already how far we can delocalize the system. That's several micrometers. That's a real macroscopic distance for our purpose, where, for example, we can shine in a laser beam in the middle. And just as a first example, we have, so that's the way we detect the atoms. For single atoms, we look if the atom is in spin state, in a certain spin state, and we get the answer either yes or no. And just the time average over many realization then reveals a typical interference fringe, and from the phase shift of this fringe we can extract the phase information we're interested in. And as a first application, we have looked at the effect of acceleration, which is equivalent, for example, to gravity. So we delocalize the atom while it is at rest, then we accelerate the system, and we want to measure now this effect of the acceleration. And to do that, we have to combine now the wave packets here while they're drifting at a constant velocity. And here you see the acquired phase difference between the two arms versus the acceleration if we have delocalized the atom by 4 lattice sites, by 12, or by 20 lattice sites. And you see that we can measure accelerations of several g with a precision of a few times 10 to the minus 4 g. And that is a first shot. We have now also some ideas to improve this even further and to really turn this into a precision interferometer to, for example, measure gravity or Casimir effects on surfaces. So you might have noticed everything I told you so far are purely single particle effects. The question is now, I told you already why, because the temperature of these atoms is still too high to really undergo coherent collisions. And that is something we want now to cure by immerse the single atoms into a quantum gas. And the idea is, so for the perspective of single atoms, a many-body system can act as a bath and cool the single atoms. And one question is, might there be a possibility to cool the motional degree of freedoms of the single atoms while preserving their internal state coherence? So that is something we want to look at. But on the other side, single atoms and the high degree of control we have obtained over single atoms might be a nice way to locally probe, detect, or manipulate a many-body system. And by that, both approaches that I introduced in the beginning might profit from this combination. But it turns out it's more than that. If you increase the interaction between those two subsystems, then it's rather, you have to rather describe the system in terms of new quasi-particles, which resemble so-called polarons in solid states, but you can enter regimes which are not accessible in solid-state physics. So now I want to explain a little bit and to show you how far we have gotten to now combine these two systems and to immerse the single atoms. So the situation we're in, everything takes place again in a high vacuum system. We have here a single atom mod at the position of these cross laser beams. We have some coils to prepare a degenerate Bose gas and some optics for fluorescence detection of the single atom or absorption imaging of the many-body system. To close up a little more, here is the position of the single atom mod, but for technical reasons, we have here a Bose-Einstein condensate in a so-called quick type trap, which is located a few millimeters away from the position of the single atom mod. And I want to first introduce a little bit the two subsystems, the single atoms and the Bose-Einstein condensate, to make clear how we take our data and what information we can get from these systems. So single atom mods, so magneto-optical traps are clear, and if you let the students play around enough, you can see they come up with nice ideas. And obviously the atoms like what we do with them, and they're dedicated to our Institute of Applied Physics at that time. And these are images of, on the average, 1,000 atoms at 100 microkelvin. However, if we now make the magneto-optical trap tighter and tighter, we come into a regime where the loading rate is extremely low. And if we look at the fluorescence versus time, then we see discrete steps. And these steps we can assign to single atoms loaded into the single atom mod. And if we do a statistics on these fluorescence, then you see we have here a histogram showing background counts, so 0 atoms, how many single atoms, 2, 3, and 4 atoms we have. What is important for the moment is that these different peaks are well separated, so we can easily distinguish a single or 2 atom in our mod. And the loading statistics here is Poissonian. That means we cannot load exactly 1 atom, but we can load probably 1 atom, and we can post-select the events. The typical temperatures here are 30 microkelvin, and I'll tell you a little later what I mean by that. Bose-Einstein condensate is rather standard in our trap. In the quick trap, we could create Bose-Einstein condensates of up to 10 to the 5 atoms of rubidium at temperatures around 100 nanokelvin. For our purpose, however, we chose a little different system. So what we do is we pre-cool the atoms here, we shuffle them to the center of the single atom mod, and there we use in the following thermal clouds just above the condensation threshold at a phase space density of 0.2. Not because we could not do a Bose-Einstein condensate, but because for the first experiments we want to get rid of any quantum effects and study the pure classical cooling, so to say, of single atoms. So now we realize that it's not easy to combine in three-dimensional space two objects with, which are 30 micrometers large. So we had to find a way to really precisely locate the single atom and the magneto-optical trap, so the single atom and the rubidium cloud. And the way we do it is shown here. We use a cross-dipole trap, and we scan one of the beams of this cross-dipole trap across the single cesium mod. And then we just see how many atoms do we load in this cross-dipole trap. And what you see here is the probability to load the atoms in the dipole trap, and so that they survive a certain loading time. And you see we have a maximum loading efficiency here of 80 to 90%, and that is limited by background collisions. Now the situation changes if we add a rubidium cloud in the center of this dipole trap, and what you see is that at the wings we have the same behavior. In the center, however, cesium atoms will not survive, and that is again an effect of these light-induced collisions, which here help us to identify clearly where the rubidium cloud is located. For our purpose, it's important to notice that here, just a few 10 micrometers away from the center, we load atoms very efficiently to the dipole trap, but at the same time they're in close vicinity to the rubidium cloud. And now the first experiment we wanted to look at was the elastic interaction between the single impurity and this rubidium cloud and the cooling of the impurity. And now the question is, what is temperature if you look at a single particle? And temperature for our purpose is always just a different translation of kinetic energy. So we measure kinetic energy and translate this into a temperature scale. And temperature of a single particle is only defined in terms of a time average. So we have to repeat this many times, and just then we get an energy distribution that we can assign a certain temperature. And that is not too different from the Bose-Einstein condensate experiments, where we have to do an ensemble average. And the first method to now extract the kinetic energy distribution is by adiabatic lowering the trap depth. So at a temperature, if we just realize a single experiment, the atom will have a certain initial energy, and now we adiabatically lower the trap depth, and at some point, at a certain energy of the trap depth, the particle can escape. And we can now map out how this behaves, this survival probability versus the energy either of the final trap depth, or we can calculate back what the initial energy was. And that is shown here. That gives us the cumulative Maxwell-Boltzmann distribution. And it shows, for example, that 60% of the atoms have an energy which is smaller than roughly 50 microkelvin. And I should stress, this is a real energy scale just divided by kb to give a decent number here in terms of microkelvin. And a fit of this distribution shows us that the atoms have a temperature on the order of 27 microkelvin. That is one way to look at this. We have a different method to determine the kinetic energy, and that is we just switch off the trap, have the system evolve for a certain time, and then we look if the atom could escape from our trap volume or not. And this we can do for various release times, and then look again at the survival probability versus the release time. And by some numerical simulations, we can then also assign this a temperature of 30 microkelvin. And this release recapture method has been pioneered in Matthias Weidemüller's group and also in Philippe Grangier's group in Palaiseau. So that is the way we extract temperature information on the system. And now the question is, what happens in our case with a single impurity in a quantum gas? So the first thing is we have to complicate the sequence a little more. Initially, we load the atom in an optical lattice and adiabatically lower the optical lattice. Then, after a certain time, we switch on again the lattice depth and do a release recapture method. And then we see from this method we get temperature of 5 microkelvin. And this cooling is just solely due to the adiabatic expansion of this optical lattice. And that is the way we had to do this, because it's not easy to combine an object which is 30 microkelvin hot with a Bose-Einstein or with an ultra-cold gas at a few hundred nanokelvin. With a 5 microkelvin, that is possible, and we can now look what happens if we put an ultra-cold rubidium cloud here at the center. So again, we adiabatically lower the optical lattice. We have the single atom oscillate through the trap with the ultra-cold cloud. We remove now the ultra-cold cloud, and in this system we again measure the temperature by the release recapture. And what we see is that already at an interaction time of a few 10 milliseconds, the survival probability is prolonged for short release times and then falls off more steep. And if we interact for 130 milliseconds, this goes further and further, here at a temperature of 500 nanokelvin. And we can now map out the temperature of the cesium atom versus the interaction time. And what you see is, first, it goes down and agrees within our error bars with the temperature of the ultra-cold gas. And I have to say that is measured by a very different method. So that's measured by time of flight velocimetry of the rubidium gas. And this here is measured by the release recapture method. And the fact that they coincide tell us we can use really single atoms as temperature probes for a gas or for another object. An interesting question is, at this point here, the single atoms were equilibrated with the light field of the magneto-optical trap, so in thermal equilibrium with something else. At this point here, also, the single atoms were in equilibrium with the ultra-cold gas. But it's an open question what the distribution, the energy distribution of the single atoms is at these points. And that's something we could not yet measure, but that's something we want to look at. Another nice feature of the single atoms is that we can track this thermalization curve at every point. So usually in large systems, it's only possible to track this if they have been already equilibrated, the two subsystems. But we are able to really extract information of the interaction by looking at the equilibration dynamics, assigning the system a constant cross-section, which is basically given only by the scattering length, and rendering here the density and the relative velocity time dependent. We can then calculate this really to see the full thermalization distribution. I'll show you that in a second. I just want to point out that's not the first experiment where single objects have been immersed in an ultra-cold gas. There have been single ions immersed in a Bose-Einstein condensate, either in Michael Kurz's group or in Johannes Hecker-Denschlag's group. There they have single ions at a final temperature of 1 millikelvin, but to my knowledge, that's the first time that a real object really equilibrates with an ultra-cold gas. So, as I want to show you quickly how we can really map out the thermalization of the system, and here is a movie of the calculation that we did. And what you see here is the density distributions of the ultra-cold rubidium cloud and the single cesium atom versus the temperature. And here you see the different time-dependent quantities in the system. And what counts now for the thermalization is this dashed line, which is essentially what I showed you before, the integral over the densities and the relative velocity. And it turns out that although the density overlap increases dramatically in the end, as you see here, it is a little bit lowered by the gravitational sag, and that's just the fact that the single atom sags a little further in our potential due to gravity than the ultra-cold atom cloud, the rubidium cloud. And moreover, the relative velocity is strongly decreased, but still we get an overall increasing interaction cross-section, which tells us that we're in a so-called running way regime of cooling. So and from this, we can really determine the scattering length. And so we could extract a value of the rubidium-cesium scattering length of 450 Bohr radii. And I give here an upper value because we have several issues that, well, make us know a lower value than we really have. And the first that you immediately see is if we release our single atom from the trap, it could oscillate in an orbit that, for example, doesn't see the rubidium cloud, so the interaction time is effectively, or the interaction is effectively lower than we think. And there are other technical issues, but this agrees very well with a recent calculation of the group of Rudi Grimm and Paul Julien, which calculated a value of 650 Bohr radii. Another thing I would like to point your attention to is the fact that during the cooling, we hardly lose any cesium atoms. That means we can, so here is the survival of cesium atoms during the cooling. If I go back, you see until equilibration, we need like 60, 70 milliseconds. And we start at 80%, and at 60, 70 milliseconds, we still have 70%, so we lose on approximately 10%. But we can use this cooling really to prepare ultra-cold single atoms. We can use the probes, as I told you, for temperature, for density of a many-body system, and I'll tell you later how we want to increase our control to really employ this as a standard tool. And importantly, we really immerse the single atoms in the ultra-cold gas, despite the strong repulsive interactions between rubidium and cesium. And that is important because if you combine large Bose-Einstein condensates of rubidium and cesium, you have usually phase separation due to the strong repulsive interaction. Okay, there is one thing we wanted to look at in the following, and that is the question of coherence of the single impurity as it is cooled, but this could not be done due to some vacuum problem. But one thing we could look at is the inelastic collisions of the single impurity with the ultra-cold gas. And usually, for an experimentalist, that is a bad effect or a dirt effect to look at losses. In this case, it very nicely shows the power that we have with our system. And we can look at every event, at every single event with single atom resolution. And at the end, I'll tell you right away, the results are not surprising because we have so few cesium atoms. The result will be there is no cesium-cesium interaction. But the tools we develop here are very sensitive tools to show the onset of cesium-cesium correlations. And at the end, we could extract a very precise number for the three-body loss coefficient for rubidium and cesium. The idea is the following. If you look for longer times and look at the survival rate of rubidium and cesium, then you see again rubidium is completely unaffected by this interaction with the single cesium atoms. That's again no surprise. You have 100,000 rubidium atoms. You have a few cesium atoms getting lost from time to time. So the rubidium cloud is completely unimpressed. For cesium, that's different. The cesium survival probability decays exponentially with time. And for the internal states that we chose here, F equals 1 for rubidium and F equals 3 for cesium, these are the absolute ground states for the respective hyperfine manifolds. And so the only loss mechanism that could be active is molecule formation. That means three-body recombination. That is known, and in large mixture experiments, that's the same. However, there it's not clear what is the mechanism. Is it two rubidium atoms forming a molecule with one cesium atom, or vice versa? In our case, that's easy to look at because we can, for example, just put in a single cesium atom. So we have post-selected this here and now looked at the case for a single cesium atom, 2, 3, and 4 cesium atoms. And we can assign then the different loss mechanisms, the different three-body recombination mechanisms that could be active. And here, what we see is that all these curves are described by the same average decay curve as in the average data set. And this already suggests that, since that's the same for a single cesium atom, only two rubidium atoms form a molecule with a single cesium atom. As I said, no surprise. However, we can look closer at here the case of two atoms, for example, and look at every single loss event and see how many atoms got lost. And that is shown here. Here is again the fluorescence trace along the sequence that we have. So here we know we have two cesium atoms loaded into our optical or into our system. Then we let them interact for a certain time, and we see how many atoms do we have left. In this case, all atoms survive after the interaction. In this case, a single atom gets lost. And in this case, no atom survives, so both atoms get lost. And again, we can assign the different loss mechanisms. And then we can see how is the distribution, the statistics of these losses versus the total survival probability, or equivalently, we could here also draw some interaction time scale. And then we plot these data points, the different statistics, probabilities of relative occurrence, and make a statistics of non-interacting cesium atoms. And we see it perfectly fits, which is again no surprise. But this method tells us very nicely as soon as we have two-body correlations, so increased two-body interactions, then we would easily see this from a deviation of this curve. But from our system is so simple, so to say, that we can very easily extract a coefficient for the three-body loss in this case. And that's, to my knowledge, the first case where such a three-body loss coefficient could be extracted for this system. And I heard rumors that there are some calculations around which lie in the same range of order of magnitude. So I want to show you a little bit the limitations of the system and what we want to improve in the future, because I have to admit that the apparatus we realized this in was never meant or made for the things we did there. And the first limitation is very clear if you look, or if you remember, that a Bose-Einstein condensate delivers an ensemble average of 100,000 atoms every minute. That's fine, and people can live with this. Single atom experiments rely on time averages, and usually in the quantum walk and whatever experiment I showed you before, you get a single result every second. And in order to get a time average, you take 100 of these images, and so 100 seconds for a data point. That's fine. If you combine the systems, however, the statistics is given by the time average and by the single atom. The cycle time is given by the rubidium atom. And now you can also a little bit feel the pain of the students in the lab that had to take the data, because one of these thermalization curves is easily a day. And so we have to do something about that, and the idea is to make a Bose-Einstein condensate every few seconds. And so that's not a mystery anymore. People have done this before. You can make the mod loading time very fast. You make an all-optical Bose-Einstein condensate, and we will also employ additional Raman sideband cooling. And by this, we want to ease a little bit the life of the PhD students and get more statistics in shorter time. Another drawback that you have realized is we have no optical resolution. But we have developed the methods I showed you before to do really single-site resolution of few atoms. This we want to implement. And finally, we have so far no selective control over the two subsystems. But what we would like to, or what we dream of, is to really be able to move the single impurity within the many-body system, to locate it at a certain point, or to even dynamically move it through the system. And the idea to do that is so-called species-selective potentials. And here is a graph that shows the idea. And it shows the dipole potential versus trap laser wavelength for the species rubidium and cesium that we use. And you see for usual wavelengths that we use, YAG wavelengths over here, we are far ready tuned from cesium or rubidium D lines. And that means the laser beam will exert an attractive potential onto both species. However, if you, for example, sit down here between the rubidium D lines, you're ready tuned with respect to the D2 line, but you're blue detuned with respect to the D1 line. So you get a repulsive and an attractive potential, and if you hit the right spot, then you'll be here at a zero crossing of the dipole potential, and strictly rubidium will see no potential from this laser beam, whereas cesium will see some potential, and we want to thereby create a potential that can move and trap the cesium atom without any effect on the rubidium system. Well, before we could do that, that's how an experiment looks if it got completely disassembled and packed up into boxes. That's something you usually hope not to see because it means a lot of work. But we had to do it because I was moving to Kaiserslautem. So we packed up everything in Bonn onto a truck, moved it to Kaiserslautem last October. We had the idea of building a new apparatus that is shown here. And this consists of a two-dimensional magneto-optical trap for fast mod loading. Here a glass cell where we have good optical resolution to detect single atoms. And I have a little movie that shows how far we got so far. So that is the mysterious building of a two-dimensional magneto-optical trap. And for the people working in theory, the vacuum is always a big issue because it's kind of voodoo. And you have to bake out and see if everything works out in the end. But here, that's the two-dimensional mod already. Here, through the big windows, we will shine in laser beams to trap lots of atoms. And here, that's the pig that is baked out here at the moment. And that's the main experimental chamber that is now attached to the 2D mod. And the vacuum system essentially is ready. Oops. So, and I see I cut a lot, but as I said, all of what I might have cut, I have in slides and backup. I hope I've convinced you that we have extremely good control over single particles in our optical lattice in terms of position, in terms of preparation, and in terms of quantum degrees of freedom. We're able to overlap single atom traps with a ultra-cold gas close to the condensation threshold, and it's absolutely no problem for us to cool further to bring the rubidium system to condensation. We've observed the thermalization of a single impurity into in an ultra-cold gas, and we see that the temperatures coincide within our error bars. And we've looked at the inelastic losses, so the three-body recombination, event by event and atom by atom, and thereby we've established a method to look very closely microscopically at the events that are going on there. So the last thing I would like to do is to introduce the team to you. So let me point out here, that's Nikolaus Spätmann. He's the guy who basically made all the experiments work, and he's the one that suffered most from our vacuum leaks just a few weeks before the move, so that very, very potentially nice experiments could not have been done. And then the rest of the team is the new team in Kaiserslautem, and they do their best to make our dream come true. And I would like to thank you for your attention, and I'm happy to answer all your questions.